Hey guys, Kenna here. Today we're going to be looking at momentum and impulse. Okay, I know we briefly touched on these before when we were going over Newton's laws, but I want to go over them in a little bit more detail here and begin to look at them in terms of what that means for collisions. Okay, so what are our essential questions for today? First two we might already be able to answer just from what we went over in covering Newton's laws. What is momentum and what is impulse? Okay. We also want to go ahead and tie it back to what we already covered and how are momentum and impulse related to each other and to Newton's second law in particular. We'll look at Newton's second law, F equals ma, and look how we can go ahead and derive the equations for momentum and impulse. Number four, how do collisions relate to the law of conservation of momentum? We looked at the law of conservation of energy already this unit, in particular looking at the idea that energy cannot be created or destroyed, it just changes forms. We have something related to that here with the law of conservation of momentum, and we're going to be thinking about those terms we gave you earlier in terms of system and surroundings as well, something that'll be really big when we get into next term. Lastly, what is the difference between an elastic and an inelastic collision? Okay, so let's start out with that first part, identifying what momentum and impulse are and figure out how to calculate those again, just to make sure you guys are familiar with it. Okay, so momentum, we talked about being defined as mass in motion. All objects have mass, that's what makes them up, and so putting that into movement is going to give it some momentum. Okay. The amount of momentum an object has is dependent on two variables: how much stuff we are going to go ahead and move. And in this case, we're looking at mass. And secondly, we're going to be looking at how fast that stuff is moving. And that's going to go ahead and be the velocity. And so this equation probably is pretty familiar to you. So again, how much stuff is the mass? How fast it's moving is the velocity. So momentum is going to be mass times velocity. And the symbol we typically use for this is a p or a rho. And so that's the symbols that we're going to look at in terms of this equation. All right. So when we go ahead and take a look at this, okay, you can see in this equation that mass and velocity are equally important when we go ahead and start looking at momentum. If one goes up and the other stays the same, momentum goes up. If the other goes up and the other one stays the same, momentum goes up. They have a direct relationship to each other. If you're holding momentum constant, if the mass goes up, the velocity goes down. If the velocity goes up, the mass goes down. So there's a very important relationship that we need to understand. We can also begin by looking at our units. Now, if we remember, mass is going to be utilized in terms of kilograms. Okay, that's our SI unit for mass, kilograms. And velocity is going to be meters per second. So this is a kilogram meter per second is the unit that we typically see in terms of a standard momentum unit. Okay. Now, that's not the only unit that you can see or use. There are plenty of others. We could use kilogram miles per hour. We could use kilogram kilometers per hour, kilogram or gram centimeters per second. These are all momentum units. But the standard one that we want to go ahead and focus on once again is that kilogram meter per second. And the reason for that is if we think about the units related to newtons, remember a newton is a kilogram meter per second squared. And so we want these units to be the same so that we can use our standard units in terms of newtons, in terms of joules. So any units are actually momentum units that you see here on this page, but we want to focus on the kilogram meter per second just so that we can get unit cancellation so that we can use things like watts, joules, and newtons. Okay? All right. So it is important to remember that mass and motion is mass times velocity and that they are equally important in determining the outcome. If we have a Mack truck and a roller skate moving down the street at the same speed, the Mack truck is going to have so much more mass and therefore it's going to have so much more momentum. If you think back to our Newton's laws videos with respect to the football players, a more massive player moving at the same velocity is going to have more momentum, which is going to make them harder to get down. And so you can kind of think of this related to inertia as well in terms of Newton's first law, because something that's got more inertial mass is going to be harder to stop. It's going to want to continue on its same trajectory with the same velocity, if at all possible. Okay. But when we start looking at this Mack truck versus the roller skate, we also have to realize that the momentum of any object that is at rest is zero because the velocity is zero and therefore the overall momentum is zero. Okay. Because they're not in motion. So that's an important thing to kind of keep in mind. So let's see the relationship between these different units. Okay. Now, let's assume that a car possesses 20,000 units of momentum. What would be the car's new momentum if its velocity were doubled? What if it was tripled? What if its mass were doubled by adding more passengers or something like that? Or both the velocity were doubled and the mass were doubled. So pause the video here and go ahead and take a look and see if you can go ahead and solve these. Okay, welcome back. So what'd you come up with? Its velocity were doubled. Remember, we want to go ahead and keep track of our equation that we've been talking about. So that's going to be P equals mass times velocity, mass in motion. And so if we were to go ahead and double the velocity, okay, that's going to go ahead and double our momentum. All right. There you go. So 2 times 20,000 is 40,000 units. So you can probably figure out what would happen if we tripled it. Okay, so if we go ahead and triple the momentum, that's going to go ahead and triple the momentum. Okay, so 3 times 20 is 60,000 units. All right, now, what if we went ahead and doubled the mass this time? So we added more passengers. What's that's going to look like? Now, if we think about this, it's no different than doubling the velocity because of the relationship of these two. And so we're going to double that. So this means we're going to go from 20,000 units back to 40,000 units. Okay, so let's look at one more example just to make sure we understand this. What if we doubled both its velocity and its mass? Okay, so this time we're going to go ahead and double the mass, double the velocity. Well, now hopefully you realize that this is going to quadruple the momentum. And so what we end up seeing is 4 times 20,000, which is 80,000 units. Okay, so that's the basic concept of what we're talking about here. If we want to think about momentum, we want to think about impulse, which we'll bring up here in a second, we can directly relate them back to Newton's laws. And in particular, we're going to go ahead and use Newton's second law to go ahead and talk about momentum and impulse. Now, when you put it another way, an unbalanced force always accelerates an object, F equals ma, speeding it up or slowing it down. If the force acts opposite the motion, it slows it down. If the force acts in the same direction, it speeds it up. But either way, a force will change the velocity of the object. And if the velocity of the object is changed, the momentum is going to be changed as well because of the velocity piece there. Okay, so we're going to have to remember Newton's laws. Now, we also talked about the fact that when we look at Newton's second law in particular, what we're using in terms of force is what we call the net force. Okay, F net equals mass times acceleration. And so when you start looking at this, we have to also remember what we learned at the beginning of the term, the fact that acceleration is equal to velocity divided by time. So if we go ahead and begin to work that out, what we end up getting is F equals ma, where a equals delta v, or the change in velocity over time. So force equals mass times delta v over t. Well, if you times the t to the other side, what you end up getting is F times t equals m delta v. So mass times change in velocity is equal to force times time. So impulse then is going to be the change in momentum. And when we go look at these equations, that's a direct derivation from Newton's second law. So on this side, we have force times time. This is what's known as impulse. And m delta v, this is what's known as change in momentum, which should make sense because remember that momentum is equal to mass times velocity. So a change in velocity is going to change the momentum, and that's equal to the impulse, which is force times time. Now, this is a point where I really like to take a look at the units. Okay, so remember, force is always going to be written in newtons, time is in seconds, mass is in kilograms, velocity is in meters per second. We already took a look at this momentum piece, and so we have kilogram meter per second. Well, let's take a look at what a Newton second is. Now remember that when we take a look at a Newton is going to be a kilogram meter per second squared. So Newton equals kilogram meter per second squared. Well, we have a Newton second. So if we take this and times it by second, cancels, and one of these seconds on the bottom cancels, leaving us with kilogram meter per second. And so these really are the same units, they really are equivalent. And so we just write them differently to recognize whether it's impulse that it's asking for or change in momentum. So the standard unit for impulse is Newton seconds, and the standard unit for momentum is kilogram meter per second. Now, why does that matter? What does that teach us? Well, if we're going to have a change in momentum, what we're looking at is how the velocity has changed with respect to the mass. Okay. Now, if we do that, what we end up seeing is that the force that's applied in a collision is going to be dependent on how long that collision lasts for. In this example, you've got a medium mass truck and it's driving in at a high velocity. That has a certain amount of momentum. Now, if we get in a car accident, what does that look like in terms of how much force is applied? Well, it depends a lot on how long that collision happens. So if that collision happens for a very short period of time, like you see in this first example here, short period of time, if we're going to go ahead and assume that this is going to be equal, because remember, P is equal to mv. And if we're going to go ahead and do it in terms of impulse, change in momentum is equal to m delta v. Okay, and we can see that our m delta v, the bigger this is, because we're going from a really high velocity to a really low velocity, what we end up having is that a force and time are going to equal m delta v. So if this is set, then this is set. But if we do it the other way, m delta v, and we set this, we have two options here. We can have a big force with a very small amount of time, or we can have a small force with a huge amount of time. And this is important if you ever do contact sports. If we're going to take a look at boxing, for instance, if somebody's trying to go ahead and hit you with an uppercut or a jab, the best thing you can do is kind of roll with the punch. As that punch comes in and starts hitting you in the chin, go with it because that'll increase the time of collision, which means the actual amount of force that you feel is going to be less. On the opposite end of that, however, you want the collision force, if you're trying to karate chop through a piece of wood or a block of glass or whatever it may be, you want that to go ahead and be as short as possible to provide the greatest amount of force with that collision. Okay. So, depending on what you're trying to do, you either want to increase or decrease the length of time of that collision to go ahead and look at the change in velocity. And this actually can be applied to our machines that we talked about yesterday. If we think about the slap of a hockey player using his hockey stick, right? You go ahead and do a very short motion on your end, allowing for a longer motion on the other end. So that's increasing the time of collision. So it requires less force to get a bigger change in momentum. And since the mass of the hockey puck isn't changing, the velocity of the hockey puck is, which means it's going to go faster. So all of these relationships are very valuable in terms of us being able to understand what happens in terms of the collision. Now, this only works because of what we know as the law of conservation of momentum. In the absence of an external force, the momentum of a system remains unchanged. And so, once again, this means we don't have any external impact on what's going on. We have the system, and then you have the surroundings. And this will be really important next term when we start looking at thermodynamics. But in order for the law of conservation of momentum to work, that means we're neglecting or ignoring what's happening external, and we can go ahead and keep all of the momentum conserved by only focusing on what's inside the system. All right. So net momentum before the collision is equal to momentum after the collision. So we say one momentum before is equal to momentum after. Okay. And again, you can write that as mv initial is equal to mv final. That's if there's only one object. But when we look at collisions, you have to realize that there may be more than one object. And so this is where we start looking at equations, and we'll talk more about this moving forward. But essentially, we have to maintain this idea of no external force in order for this to be true. All of it takes place inside the system, and we're not worrying about the impact on the system from any external surroundings. Okay. All right. Lastly, there are two types of collisions that we're going to be exploring. These are elastic and inelastic collisions. Now, when we go ahead and start looking at these two types of collisions, it's going to be determined based on whether there's loss of energy or that energy is converted. And then when we look at calculating them, it's whether the objects stick together or whether they don't stick together. Okay. And we'll show you examples of both of these. But in the most simple sense, the difference between elastic and inelastic is that in elastic collisions, the momentum is conserved because there is no heat loss or deformation of the objects. So, like a car accident would not be a truly elastic collision. If you can hear sound, that's not an elastic collision. So, the Newton's cradle that you often see when demonstrating Newton's laws is not going to be truly elastic, even though in some cases it simulates that. Because if you close your eyes, you can hear that little click, 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 click. And every time you do, that's a little bit of transfer of heat, a little bit of transfer of sound, and sound and heat energy are lost from the system, meaning it's no longer going to be maintained. This is why a perpetual motion machine never really exists. Doesn't it work? Because you are always going to lose some of that energy to the surroundings. So, as we mentioned before, elastic collisions, momentum is conserved, no heat generated or deformation of the objects. Okay? So, in the example you see below, velocity is 10 coming in, the other one is at 0, so we have 10 velocity. And then they collide and stick together. Now we've got twice as much mass, and so we've got half as much velocity. In an inelastic collision, momentum is conserved because the colliding objects become distorted and generate heat during the collision. When we were looking at those football collisions, when we were going over Newton's laws and in the NFL, those have lots of sound produced. Those have lots of heat and friction produced. And so these are definitely inelastic. Okay. You can see these trucks down at the bottom actually go ahead and have some deformation. There's the little heat and sound waves coming off of them. Those are a good example of inelastic collisions. Okay, in a perfectly inelastic collision, both objects would end up sticking together. Uh, but in most cases, in real world situations, you don't have truly elastic or truly inelastic. And we'll go ahead and start taking a look at how these work in another example. All right, guys, take care of yourselves. Stay healthy, stay safe, and we'll talk to you soon. So long.